as a simulation engineer, you sometimes miss this connection with the reality. When you work together with test teams, you are able to see what's wrong in your model, what can you update in your model. So it's like it creates some connection to the reality. This is what we need, because indeed we can simulate a lot of things. They can be fancy, beautiful simulations, but without this correlation, it's worth nothing. So in acoustics, in vibrations, when we are talking about electric motors, they have very, very high rotational speeds. They can go up to 20,000 rotations per minute. So we are talking about very, very high frequencies. And all these vibrations, if they are excited by the electromagnetic forces of the motor, they are not masked in the electric vehicle because there are no other sources of noise. And this is why it is very important when we are working on an electric motor to make sure first that there are no resonances happening in the structure. So when you connect, for example, your electric motor to the frame, that nothing is vibrating. But what we can do, and what is done a lot for complex structures like tires, like compressors, is that we can actually measure the component. We can measure the structural forces of the component. This is something that we call blocked forces. We can measure, we can input these blocked forces into simulation. Because as a simulation engineer, you don't want to deal with the compressor. You don't want to model the compressor. It's a very complex structure. So you can measure it, and you can use these forces for your simulation to see how the structure responds to it.
So the hybrid method where you have a numerical model. Some parts of that model will be based on traditional finite element representation, and some parts will be a numerical response that you've obtained from a physical test.
If you're an engineer, you still have this basic logical thinking. And so if you run a simulation and if it gives you some strange results, you will ask questions. You will doubt your results. And this is why we have support teams. This is why we have trainings. So I think it should be accessible to everyone.
In this episode of the Simulation Stack, we feature Alina Lysak, a business development professional at In Summa, a Hexagon partner in Benelux. From her native Ukraine, Alina studied mechanical engineering in France before embarking on a career in the automotive industry, specifically around NVH and acoustic simulation. In positions with Continental and Lightyear, she gained key skills in motor and gearbox design and looked at their influence on electric vehicles. In our conversation, we spoke about the need to consider vibration and acoustics at an early stage in EV development, her work driving new business at In Summa, and areas where she sees simulation advancing. Cool. Okay, Alina, lovely to see you today. Thank you for joining me.
Thanks for inviting me. It's an honor.
No problem. So one of the things I normally ask people when we get started talking is perhaps you could just give us an idea of where you are in the world, first of all.
Yeah, it's a good question. I think I'm a citizen of multiple countries. So I'm originally from Ukraine, and when I was 18, my parents sent me to France to an engineering school. So I did my engineering studies in France, in a small town in the north of France, in Rouen. And I studied mechanical engineering for 5 years. And then I started to work directly in France. I worked for 5 years in France, or even a little bit more, 6 years. And then I went to the Netherlands. Okay. And so now it's been almost 3 years in the Netherlands.
Yeah, gotcha. Yeah, I noticed that I was looking at your resume, and I think you've listed 4 languages: English, French, Ukrainian, and German as well.
Yeah, and Russian
as well. And you had a little like a slider bar for proficiency, as it were. And so you don't speak Dutch then, or do you not need to in daily life? Would you say?
I live in Amsterdam, and I speak a little bit of German, so I just understand certain words in Dutch.
Okay.
But in Amsterdam, it's so international here that you don't really feel the need to speak Dutch language. Sometimes you have these letters coming from a tax office, for example, and you actually need to understand what's happening there. But otherwise, I don't think it's really it's not a problem for me.
Yeah, Gotcha,
Yeah,
gotcha. I mean, that's one of the downsides of somebody like myself who's been brought up in the UK.
yeah,
You speak English, that's
yeah,
it.
yeah, yeah. But that's a good thing. Then you understand everyone because everyone speaks English, so it's good.
Yeah, but it would be nice to speak Ukrainian or French or whatever.
They are beautiful languages,
Yeah.
yes.
My son, just briefly, my son is 14 years old and he loves learning Spanish at the moment.
Hmm.
So I'm just getting
I,
my head around
I'd
around
love
that.
to. I'd love to learn Spanish. It's very practical, and I think if you would like to be an automotive engineer, it's very, very important to speak German actually. And this is why I started to learn German because
Yeah.
we worked a lot with our German colleagues, and all the automotive industry is in Europe is there. So it's actually very handy to speak German.
Mm. Yeah, of course, of course. Cool. Okay. So at the moment, you're working with In Summa, one of the Hexagon resellers in EMEA, or in Europe, based covering Benelux, I think.
Yes,
Yeah.
Benelux.
But I just wondered if you could. So you mentioned your mechanical engineering studies
Yes.
in the north of France. So you tell us about the some of the early career positions that you held once you'd qualified
Mhm.
from university?
Yeah, so at university, we had to choose between three specialties: computational fluid dynamics, structural mechanics, and production. And I decided to go for structural dynamics because I was so obsessed about crash simulations. I thought like it's really, really beautiful to do crash simulations. And this is why I chose this specialization. And right after that, so we did quite a few simulation projects at university. We also worked a little bit on optimization and correlation between the your simulation and tests. So we had some basic knowledge on Mach criteria, on frequency response functions correlation. And when I graduated, I was looking for a job, and there was a small company right next to the university, and they had a simulation team and a test team, and they had a pretty big test facility. So they had an acoustic room, a few rooms to do model analysis, experimental model analysis,
Yeah.
and they were looking for simulation engineers to work on different projects. So they mostly worked with Renault in France, with PSA sometimes, and they were doing different kinds of simulations for these companies.
Mm.
And I started then as a simulation engineer there, and it was really perfect because I think as a simulation engineer, you sometimes miss this connection with the
Mm.
reality.
Mm.
And when you work together with test teams, you are able to see what's wrong in your model, can you update in your model. Um, so it's like it creates some connection to the reality.
Yeah.
This is what we need because indeed we can simulate a lot of things. They can be fancy, beautiful simulations, but without this correlation,
Mm.
it's worth nothing.
Mm. Yeah, absolutely. No, that's great that you're in an environment where you're closely involved, or you can at least speak with people who are involved in the
Mhm.
physical world, you know. I mean, I remember what one of my early jobs, I was working with an aerospace supply company who were manufacturing composite components. They were making the air intakes for helicopters, so
Mhm.
really interesting composite structures, and they had heating elements within the laminate to stop ice forming. And we were in a sort of reasonable sized building, but we had a simulation team, we had a test facility,
Mhm.
both in terms of product test and also material qualification. And we also had, obviously, we had CAD designers as well, but we also had the clean room where people are making those physical composite parts.
Okay.
So we could really join the dots between, design, manufacture, and test. And that I think, like you say, the ability to bring all those things together
Yeah.
is really important, isn't it? And again, we mentioned this before we hit record, that in the world of simulation, because we have this, multitude of different physics available to us, computing systems, software, blah, 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 it's sometimes very easy to forget why we're doing this stuff in the first place, So yeah, okay. So you had an initial position in France then?
Yes.
Yeah. Okay. Okay.
As a simulation engineer, so I worked for different projects, and then I was sent to Toulouse to work for Continental
Oh, okay.
for electric motors, and
Yeah.
we were working on correlation of the finite element model of electric motors.
Yeah.
First, I was working there as an external employee, and then
Yeah.
they hired me
Okay.
for this position.
Yeah. 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 Cool. So what type of application were those motors aimed at then?
Yeah, it's a very interesting application, I would say. It's maybe a little bit different from internal combustion engines because you work with different frequencies. So in acoustics, in vibrations, when we are talking about electric motors, they have very, very high rotational speeds. They can go up to 20,000 rotations per minute. So we are talking about very, very high frequencies.
Yeah.
And all these vibrations, if they are excited by the electromagnetic forces of the motor, they are not masked in the electric vehicle because there are no other sources of noise. And this is why it is very important when we are working on an electric motor to make sure first that there are no resonances happening in the structure. So when you connect, for example, your electric motor to the frame, that nothing is vibrating.
Yeah.
And this is what we were working on. And one of the biggest challenges we were trying to solve is actually this link to the reality. We wanted to correlate our electric motor finite element model up to very high frequencies, up to 7 and even 10 kilohertz, which is like quite a huge task.
Yeah. Yeah. Okay. What software were you using for that kind of work?
Oh, quite a few software. We used ANSYS, but not the Workbench. ANSYS.
Classic, was it?
Classic, yes,
Yeah.
yes. Because of its flexibility, and you can write the script yourself, so you can control what's happening.
Yeah.
So mainly ANSYS, yes.
Okay. Okay. And in terms of the electric motor for vehicle use, I mean, Toulouse. My background is in the aerospace industry, and Toulouse is a massive hub for Airbus for their
Yes.
final assembly line. So I always think of Toulouse as being an aircraft city. So was there any crossover between what you were doing on the electric vehicles with the aerospace applications then, or were they completely separate?
I would say completely separate, but it is indeed true. When you go to Toulouse, when you take an average guy on the street, they will tell you 90% I work for Airbus, either as a supplier or as an external or directly for Airbus. So it's very true, but there are also other companies, and Continental was quite big there. They had a production line, and there were like 3,000 employees in Toulouse, internal employees. But otherwise, I don't think there's any connection. But of course, Toulouse is a very nice city for this industry because I saw it once. It's quite nice. They launched Airbus XL, like the super huge big plane.
Yeah.
I think it's the Beluga one, or
Yes.
and there was an XL size, and it was the first flight of it. And everyone was on the streets, everyone was watching, everyone was so happy and excited about it. So it's really like, even if you don't work directly for Airbus, you feel this connection.
Yeah. So you've seen the Beluga take off
Yeah, the huge
from Toulouse.
one.
Well, an interesting point. You probably can see from some of the stuff on my shelves. I'm from North Wales originally,
Okay.
and Airbus in the UK manufacture their wings very close to where I grew up.
Okay.
So we used to see the Beluga all the time.
Ah,
It
nice.
would come in. So the A380 originally, the wing was too large to be transported by air. So it was put on a barge and sailed around the UK onto the west coast of France and then driven across France.
Wow.
But then the advent of Beluga and some of the wings. So I don't know if you know the Airbus industry, but the aircraft industry, but the A350 is the sort of last big commercial project that they've done. That is flown directly to Toulouse from the facility in North Wales. So there you
Okay.
go, joining the dots in the world. Yeah,
Yep.
that's cool. So I know Continental from their tires. So is it the same company or
Yes, it is
different
the same thing.
divisions? Yeah,
Different divisions, yes.
yeah.
So they are mostly known for tires, of course, but
Mm.
they started to develop electric motors, control systems as well for vehicles.
Mm.
And I worked at this powertrain division. So they developed an integrated system, electric motor plus inverter plus gearbox, and it all was sold as one unit, basically.
Okay. Yeah.
I was working on on NVH problems of the electric
Yeah.
motor and eventually gearbox.
Yeah.
So we came to the point where we had to do something with the gearbox because of gear mesh misalignment. It could produce some noise as well and transfer the vibrations to the car.
Okay. So if they're selling those those systems as a single motor and gearbox unit,
Yeah.
do they exist in some of the commercially available cars that we know today? Then do you know which cars they're in?
Yeah, I think it's Peugeot E208, E208. And we were working a lot with Chinese companies,
Okay. Yeah.
but I can't tell you more because I wasn't involved. I was actually in R&D department,
Yeah.
so it's like a very, very slow pace, and you
Yeah.
go
Yeah.
into technical details, into all the simulation details, and then
Yeah.
there are some activities happening, some projects happening, but you are still staying like as an engineer um, in your work.
Yeah. Okay. I mean, it sounds going back to what we're talking about, the correlation between simulation and the physical world. You've got a very interesting structure there, haven't you? From a plain engineering perspective, you mentioned, things like durability, noise, vibration, which are, perhaps not the most complex problems that anybody's ever solved, but there is an element of difficulty with those kinds of analyses and how you handle the model build and, all the solution of that. But the fact that you can then compare that directly with what's coming out from, component testing or vehicle testing is pretty nice environment to be in. That.
Yeah,
Yeah, yeah.
indeed.
So you moved. You then left that company and went somewhere else. So why did you decide to move on?
Oh, I think I missed some excitement because,
Okay.
as I said already, when you work as a research and development engineer, and big companies, they normally have R&D departments. And as I said, the pace is very slow, so you go really deep in details. Sometimes, if you're lucky, you can travel, so you can present your work at different conferences. But then it doesn't happen that often. But if you're lucky, you can do that.
Yeah, yeah.
And last year at Continental, I worked on a project, very interesting project. So the goal of this project was to use 1D simulations to find the most efficient combination of the gear ratio, the motor, and the inverter for an electric vehicle for WLTP. And
WLTP.
yeah, it's
Sorry,
a
what's that?
it's a certain let's say when you take a new car, BMW, they normally write CO2 emissions in WLTP.
Oh, I see. Okay.
And this is a certain cycle that the vehicle follows. So it gives you the speed of the vehicle. So it goes to 50, it goes back down, it goes to 70, it goes back down, it goes to 130. And this is what they would use to represent the driving cycle of a vehicle in the
Yeah,
city and on a motorway.
yeah. Gotcha.
It's just
Gotcha.
a profile of speed for your car. And I was doing a little bit of market research to see what's happening, what type of motors are used, what type of inverters are used. And I found this very interesting company in the Netherlands, and it's called Lightyear.
Okay.
Like, wow, what they are doing is absolutely mad. Like, I've never seen anything like this. So it's the first solar electric vehicle in the world. And it's a very interesting story, actually. So 5 students from a university, they decided to start a company that makes solar electric vehicles from scratch. So they had to rethink everything. And what they came up with is, so we are going to use 4 in-wheel motors because it will make the car more efficient. We are not using any gearboxes, any transmissions at all, so we don't have any energy loss in those systems.
Yeah.
If it's connected directly to the wheel,
Yeah.
efficient system. So there was this one solution. The second one is that they had like the lowest drag coefficient on the market. It was around 0.17, something like this. So the shape of the car was also very advanced, I would say. So the goal was to create a very efficient and light car with this solar roof on top of it. And the idea was to give around 70 kilometers per day just by solar power.
That's amazing. And
Yeah.
is this a product that people can buy now then, or are we still in the development phase, or what's happened?
It went bankrupt.
Okay.
It went bankrupt 1.5 years ago.
Yeah.
And the last price that I remember, they wanted to sell this car for 250,000 euros.
Yeah.
But because of many reasons, it didn't. Yeah.
They've probably hit the market too soon, haven't they? The market isn't ready. The technology's not there to allow that car to be made at a cost. I mean, you know, that's a Ferrari price, isn't it?
Exactly.
You know,
Yes.
you know,
And what I can say as an NVH engineer, when you buy a Ferrari for that price or any luxury car,
yeah,
you feel that it's luxury. You feel because there is a good noise insulation, because nothing vibrates, because you hear nice sounds.
yeah,
But like the problem of many companies, fresh companies who are trying to develop a product, is that they do not consider NVH at early stages of their development. It's noise, it's comfort, it's not that as important as efficiency, for example.
yeah.
But the problem is if you don't design your structure with thinking about NVH, then when you're about to freeze your design, you'll potentially find some problems, and then it's too late to redesign. So you will have to put some dampers or do something else that will add weight to your car, and that would you could avoid this if you would have thought about it at the beginning of your design.
Yeah. Okay. So was it the case then that when the initial product was available for people to buy, the experience wasn't really worthy of the 250,000 euro price tag then? Is that a fair description?
I think that there were many different factors. As an engineer, I didn't really care that much about all the different financial factors. The car was manufactured. There were like 2 or 3 cars. But then, well, it went bankrupt, so nothing else happened. There was Lightyear Zero, this first car that they were designing from scratch with 4 in-wheel motors.
Yeah.
And this car they wanted to sell for 250K, and there was like a limited amount of these cars, like few hundred cars.
Yeah.
And we started to work on what we were calling Lightyear 2, so a small car with less technologies in it that would still use solar roofs. And we were like working on NVH criteria for this car, NVH requirements for this car, how to define them. And then, well, it didn't happen.
Yeah. Okay.
This
So
car would be cheaper.
Yeah. Okay. Okay. So, I mean, that's obviously there are many factors. There's commercial aspects, there's manufacturing aspects,
Yeah.
but what you sort of pertained to there was that there were issues with some of the MVH or the driving experience. So, with hindsight, do you think they should have put more emphasis on the MVH from a simulation perspective earlier on within the product development?
As an NVH engineer, I would say yes.
Right.
But I understand that as a company, sometimes you don't have time for this and it's not your priority, and it's totally fine
Yeah.
because NVH simulations, they require a lot of time and a lot of efforts.
Mm,
You can't just run a simulation in 1 month. You need to find the right software, you need to find the right workflow, especially if you work with something innovative like in-wheel electric motors.
mm.
Nothing you can use. There are no publications, so
Mm.
you should develop everything from scratch yourself.
Yeah, 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 yeah.
Um, yeah, so I would say please consider NVH from the very early stage of your design, but of course it's not possible.
Yeah, yeah. Okay, okay. I mean, from my perspective, in the aerospace industry, the design cycle or the development cycle for a new aircraft is multiple years. Seven,
Yeah.
8, 9, 10 years or something for a new aircraft, maybe even more than that. Um, and I've worked in environments where looking at using legacy methods, analytical methods, legacy software, this kind of stuff
Mhm.
really hampers the development. So a lot of the work I've been doing, in the past few years has been looking at tools like Apex, tools like Nastran run in a much more efficient manner. So you can build, verify, modify, and update a model in a fraction of the time that we
Mm.
could do you know, in again using legacy tools. Obviously, some of them are Hexagon tools, some of them are third-party tools that we know the names of course. But I mean, with your insight into some of the products you've seen now with In Summa, skipping forward perhaps a little bit, but could you see or would you been able to pinpoint opportunities where you could compress that development cycle?
Yes.
Yeah, yeah, okay, okay, that's interesting.
Yeah, that's a very good question actually, because there is kind of a new tendency that we are working on in NVH, and it's called hybrid methods in acoustics.
Yeah,
And our development team, Actron development team, puts a lot of efforts in it,
yeah,
and I think it would help a lot. The only thing is that you need a prototype. So what we normally do with pure simulations, you have your structure, you build your finite element model. Without a prototype, you can't really correlate it, so you don't know if it's a good model or a
yeah,
bad model.
yeah,
So you can rely on your experience maybe, and then you can do certain investigations with this model. Frequency analysis, yeah, like maybe surface velocity analysis. And this typically takes a lot of time, and the result, maybe you will be able to give the tendencies in your results. For example, with this model, you will have a better result than with this model in terms of, for
mm,
example, sound. But what we can do, and what is done a lot for complex structures like tires, like compressors, is that we can actually measure the component. We can measure the structural forces of the component. This is something that we call blocked forces. We can measure, we can input these blocked forces into simulation. Because as a simulation engineer, you don't want to deal with the compressor. You don't want to model the compressor. You don't want to
yeah, yeah, yeah,
it's a very complex structure, so you can measure it and you can use these forces for your simulation
yeah.
to see how the structure responds to it. You have
Okay. So the hybrid method
the hybrid
is
method.
where you have a numerical model.
Yes.
Some parts of that model will be based on traditional finite element
Yes.
representation,
Yes.
and some parts will be a numerical response that you've obtained from a physical test. Is that
Yes.
is that a
Yes.
good way of describing it? Yeah. Okay. Okay. Yeah. I've not really come across anything like that in general terms, but yeah. Okay. That's pretty interesting, isn't it?
It is very interesting. I think it's also very handy when it comes to complex structures. Here, for
Mm,
example, if you work with tires, and tire noise is very important for cars, for automotive industry, because
mm,
this will tell you how to choose the passive acoustic treatment of your car. And modeling tires is difficult. You
mm,
don't have all the data from the suppliers. There are so many materials. You have to consider so many physical effects when you model your tire. So it's easier to to measure your tire. And when you
yeah.
measure it,
Yeah.
you can
Yeah.
also do acceleration, deceleration. You can measure certain operational points. All this
Mm,
data will be available for your models.
mm. Yeah. Okay. So in terms of the technology that we're talking about here, can these methods be integrated into Actran, presumably?
Yeah.
The Hexagon acoustic solver,
Yes.
and
Yes.
then that Actran behavior can be incorporated via some kind of co-simulation with the Nastran NVH models. Is that something that you could do then?
This could be done as well. And there is a very interesting project that we are developing here with Actron team and with Microflow team. Microflow is a company in the Netherlands, and they make acoustic intensity sensors. So they will be
Okay.
able to measure the acoustic intensity of your part.
Yeah.
And once it's measured, it can be smoothly integrated into Actron. And you can do far-field sound radiation
Mm.
simulated with this data.
Yeah. 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 Okay. Okay. Cool. Okay. So we've crossed over a little bit from Lightyear into your work with In Summa, but perhaps if we just take a tiny step back. So what I mean, obviously, it sounds like you enjoyed working at Lightyear, but circumstances out of your control meant that you'd have to be looking around for something else. So what attracted you to work with a software reseller and In Summa do some consultancy work as well?
Yes,
Yeah.
yes.
Okay. So yeah, what was it? What did you see were the good points of going to work for In Summa compared with maybe another automotive company or something like that?
I knew In Summa before. I presented my work on tire noise and electric motor noise at one of the events.
Oh, okay.
So I knew already people from there, and I worked with them for Actron. So they
Yeah.
sold me Actron, and I was at Lightyear.
Oh, okay.
Yeah. And well, it's a little bit personal decision because as an engineer, as I said, you have to be really lucky if you want to go somewhere, visit different countries, go to events and present. You have to be well connected with your management, maybe, and have this
Yeah.
freedom to do so.
Yeah.
Um, and I missed this connection with other people, with colleagues. I really like to meet people, to discuss
Yeah.
to know what we can do, to see what their challenges are. And In Summa had an opening, and the opening was business development position. And so I applied, and they decided to hire me.
Yeah. Good stuff. Good stuff. And were you based in Amsterdam when you were with Lightyear as well?
Yes, yeah,
So
Amsterdam.
so there was no change of geography for you.
No.
It was quite a straightforward transition. Yeah. Okay. Okay. Cool. Okay. So obviously in your business development role within Summa, I know a little bit about the company and some of the people that you work with. But one thing that struck me about some of the marketing, the outbound marketing that you've been involved with, and some of the events and some of the LinkedIn posts that I've seen you do, you really try and emphasize how different technologies can be brought together to solve some quite tricky problems.
Mhm.
Um, and there's I, I can't remember which car it was, but you use an example of a car door
Yeah,
slamming closed in terms of
yeah,
the structural behavior, the kinematics, the noise or the acoustic impact. So that's something that you're pretty keen on promoting then in terms of the Hexagon portfolio, but just in general interest terms, you like
yeah.
bringing those technologies together.
This is something that inspires me, and I think what is fascinating about the simulation world is that simulations are behind everything today. You take a shoe, a sports shoe. How much development is in the design of the shoe itself? They spend hours, days, and weeks in finding the right shape of the shoe.
Yeah.
And same with noise. And even like at Lightyear, I was just about to give my feedback on the NVH impact of the side mirrors of the car.
Yeah.
And this is absolutely fascinating. It's like how people develop these methodologies, quite complex methodologies, to solve these engineering problems. Because, for example, what happens with the side mirror is that when the car drives, it creates a certain vortexes behind the mirror.
Yeah.
And only like small components of this vortexes will go through the window and you will hear it. So what you hear at high speed is normally wind noise, but you can simulate that. And you can also choose the right design of your side mirror. And I think this is so cool. You can put simulations everywhere. And I think simulations are here to help us to design the right product.
Yeah, absolutely. I mean, that you just got me thinking now about, you mentioned a shoe as an example,
Yeah.
a product which is ubiquitous, it's everywhere. One of the very first practical examples I looked at from a simulation perspective was in the development of the machines that make corrugated cardboard. So cardboard with the wave and the sheets, a piece of cardboard. It used in packaging, paper packaging.
Okay.
Yeah, I'm just trying to think if I have an example here. But if you take a paper box and you have that
Yeah.
shape.
Okay.
So I was looking at research element into the efficiency of that process. So
Wow.
you have these very large gear wheels,
Yeah.
tiny teeth that shape the paper and then bond it to the faces.
Okay.
And nobody ever thinks about the design of a cardboard box.
Yeah.
It must be the most simple product that you could imagine, but there is a huge amount of work that goes into obviously the structural response, whether it's strong enough, whether you can recycle it, whether how easy and efficiently you can make it, but perhaps most importantly is the raw material usage. If you can reduce the amount of material that goes into that thing,
Yeah.
you can be saving companies millions and millions of pounds,
Exactly.
dollars or euros or whatever. But yeah, it is interesting. We're talking about, on one hand, Lightyear, a solar powered EV, electric vehicle
Yeah.
on one hand, and on the other hand, a shoe or the box that the shoe goes in. It's everywhere, isn't it?
It is indeed. Yes. And you can simulate everything. And we have for this internal sales site for Hexagon.
Yeah.
And there were like people simulating the fish, how the fish was like swimming through the water.
Yeah.
Everything.
Yeah. No,
Indeed.
fantastic. Yeah. Okay. So in terms of all the work that you've done, so the work you're currently doing with In Summa, and the work you've done previously with Lightyear and Continental and your university studies, what are some of the best applications or the things you're most proud of in terms of what you've been looking at, would you say?
I have something funny to show you, but I'm not sure. Can I share my screen? Do you think it's recorded?
It will be tricky to edit that in, I think. But yeah, perhaps if you can just describe in your own words, if that's all right.
Okay, so I can give you two good examples. The first one was at Continental, and we were working on optimizing an electric motor in terms for NVH behavior. And so first of all, as I said, you need to correlate your finite element model with test results. And what we achieved was quite impressive because our model was pretty good till 7 kilohertz. And this is like very, very good result.
Yeah.
And then there was an entire optimization workflow that we developed. And the workflow was to find the right shape of the inverter cover. And when you talk about NVH, the worst enemy of NVH is a flat surface because it will vibrate. It has so many different
Okay.
eigenmodes
Yeah,
at
yeah.
frequencies, and with rotation machines, they will excite all the frequencies because of the rotation speed. They go from 0 to 16,000 RPM, so we excite all the frequencies. So there is a big risk that all these eigenmodes will be excited on the flat surface. And this is why we would like to avoid flat surfaces.
Okay.
And when we take this unit that Continental developed, electric motor plus inverter, the inverter cover is a flat surface made of steel, I think it was made. And so the big question that we had was, how can we optimize this cover so that it makes less noise, maybe in these frequencies, for example. So we take a frequency range from 500 to 600 hertz, and we want to reduce the noise produced by this cover.
Yeah.
And so we run some, it wasn't topology optimization, it was a topography optimization. So when you have a flat surface, you can't really optimize the shape, but you can optimize the levels of your surface. And we ran the optimization, and the result that we got from it was actually just a nice result. Because it looked like an alien. So you have like an alien shape on your inverter cover. So it's a shame I can't show you, but it's just like, I think it's nice to see.
Yeah. Okay.
Crazy shape that you can get with your optimization.
Yeah. So were you varying the depth of the surface or the thickness of the surface?
The depth.
The depth. Yeah. Okay. So you were punching a shape.
Yes.
Yeah. Okay. Yeah. So in terms of the optimization, then did you have some means of the mesh changing position?
No, the mesh wasn't changed. No.
Right. Okay. So were you looking at maybe the offset of the shell properties?
Yes.
Yeah. Okay. I see. Yeah. So you have a fixed mesh.
Yes.
And then a variation in property.
Exactly.
Yeah. Okay. So you called it topography.
Topography. Yes.
Topography. Yeah. Okay. So again, there are many top optimization strategies. So topology, topography, topometry, I've heard of as well. Which use slightly different approaches. But yeah, that's really interesting, isn't it? When you use a high level mathematical and numerical solution technique to solve, I wouldn't say a basic problem, but something which is flat, that you've now changed the profile and improved the performance of the product. Yeah. Okay. No, that's pretty cool. Yeah. Good stuff. Cool. Okay. Right. Well, we've been speaking for quite a while, actually. I have a little clock here. I'm just keeping an eye on. Before we finish, is there anything? Oh, well, where do you see simulation heading? I know this is a very big open topic, and before we hit record, we in fact you used the term hype when we were describing AI and multi-physics and all these different things. But again, with your role in business development, where do you see things going?
I see that there is a lot of so if we are talking about machine learning, artificial intelligence, I see that there is a lot of efforts going from our development team to develop these products. And there is some interest from our customers. But when it comes to the point like, okay, let's give you a trial license, or let's demonstrate you how it works, then what I see is that engineers would rather prefer to stay with their old methods and not to try something new, maybe because they don't have time, or maybe because they don't trust it enough.
Yeah.
But I see there is interest, but I see that nothing is happening with regards to this.
Yeah.
So that's one thing. And the second thing, I think it all goes to what is the right term, democratizing.
Yeah. Yeah.
Yeah, because we see, for example, if you take Actron, the user interface was quite complex before, but the team made a lot of progress in making it very user-friendly.
Mm.
What we would like to see and what we see a lot, that companies, they see the potential of using simulations because there are a lot of tests, and tests are expensive and they take a lot of time. So of course it makes sense to run simulations. And the software should be just it's like a tool. It's like a hammer. You take a hammer, you want it to be efficient, you want it to work, right? So that's what I think would make sense. And we see a lot of efforts from the development team to make it user-friendly. Apex is an amazing example. I think the graphical user interface is fantastic. It's like so modern and nice. And this is important. It should be easy to use. And well, do you really need to understand all the theory behind, like all the equations? What is a Jacobian? Like, I, I
Yeah.
think,
Yeah.
yeah, if you're an engineer, you still have this basic logical thinking. And so if you run a simulation and if it gives you some strange results, you will ask questions. You will doubt your results.
Yeah.
And this is why we have support teams. This is why we have trainings. So I think it should be accessible to everyone, to every engineer, at least.
Yeah. That reminds me of a comment that one of the previous guests came up with or used, where he said that he believes every simulation is guilty until proved innocent.
Yeah, okay.
You know? So irrespective of what you see, you have to assume it's wrong until
Uh-huh.
you've proved it's right. You know, I think
Makes
that's
sense, makes sense.
that.
Yes.
But again, obviously, you know, things like software, ease of use, and training, and you know, experience make that process of proving a model is correct, make it easier, don't they? You know, but it's still something that people always, I believe, always have to query that, you know, is what I'm seeing from my FEA or acoustic or whatever method I'm using, does it make sense, and is it going to help me? You
Yeah.
know?
But I think also, I've been thinking about this question, and well, I have this proper education. I studied mechanical engineering. I did some simulations at university, but it was always from theoretical side. So I only changed oil in my car like 2 years ago. Before that, I didn't know what like how it works. I didn't
Yeah,
touch it with my hands. But I think if you are like a proper mechanical engineer, what I say, like proper, if you do things with your hands, you will be able to understand easily what happens with simulations. So maybe I'm saying it because the grass is always greener on the other side, and I think that these guys, they have maybe some advantages compared to me with my theoretical background. But I think it should always be like a hand in hand, your hands-on
yeah,
experience and your theoretical background.
yeah, yeah. Good words indeed, Alina. Thank you. Cool. Well, it was lovely to speak with you. That was really interesting. I'm sure lots of people will enjoy hearing, you know, the conversation and some of the things you've spoken about. Lots of really interesting stuff there, you know, in terms of the work you've done with electric vehicles and the correlation and, you know, the ability to bring that knowledge into a sort of high level software environment with the work you're doing with In Summa. So
Yeah.
thank you for your time.
Thank you so much.